been a big journey getting this all done. I think I have enough footage for at least one more video where I make the threading dial as kind of an add-on. Keep your eyes peeled out for that. Hey guys, welcome to my channel. If this is your first time to the channel, my name is Kevin Toppenberg and I have been restoring a 1935 South Bend lathe. And on prior videos, I've actually finished the restoration. I encourage you to go look at those. But this time we're going to talk about a threading dial. Now, threading is something that machinists do when you want to cut threads so you can put a nut on or tighten something up. One of the important tools that you need to do that is called a threading dial. So today we're going to talk a little bit about the theory behind threading dials because frankly, they confused the heck out of me. And I took some time and tried to figure it out, and I'm going to share with you what I've learned. And then we'll go through the manufacturing of the one I made for mine. So come along. Now, one of the first things you may say is, what the heck are you talking about making a threading dial? Don't all lathes come with a threading dial standard? And yes, they do now. But back when this was made in 1935, I believe it was an add-on because I was able to actually find on eBay some pictures of someone selling some new old stock in a box of the add-on threading dial that you could get for the lathe. So those pictures are pretty cool, but that means I don't have one. Now the internet and eBay are full of add-on threading dials. Looks like it's a long-standing tradition to make your own. So I'm going to roll up my sleeves and see what I can come up with. I spent quite a bit of time today designing this little gear to be used in a threading dial indicator. And then this will go along here. And as the carriage moves back and forth, it'll rotate the shaft. And what took me so long to design was kind of wrapping my head around how the gears work. If you have two gears that have the same threads per inch, usually they'll mesh. But meshing gears where they roll in and out is usually an involute gear issue. This is a trapezoidal or an Acme thread. So different kind of threads work differently. Like on a bolt, there'll often be a point. With the trapezoidal, it kind of goes up, flat top, and down. And then involute gears, they have kind of a rounded tooth profile so that as the gears are rolling in, they have a kind of a continuous surface. But when you have an involute gear and then a trapezoidal gear, they don't necessarily mesh exactly right. But because this is plastic and there's not going to be a lot of stress that's put on the gear for a thread dial indicator, if this just wears out, it's not a big deal. I can 3D print another one. The other thing that confused me was why, okay, so I made a model of the trapezoidal pattern at 6 threads per inch, and then I essentially played around, and it turned out that this thread here is 20 teeth per inch. And I tried higher, lower, and tried to look at it, and it seemed like 20 TPI is what matches up with a 6 threads per inch Acme thread. That makes no sense to me. Wait a minute. Some of my viewers are not machinists. So as I'm editing, I realize I haven't really explained why we care about all of this. So imagine you have a tool and you're going to cut a groove in a shaft and you're going to ultimately make threads. You don't do that all in one pass, at least not on a lathe. So you cut one pass and then you're going to back up and you're going to cut another pass. And it's very important that you have that tool synchronized, because if you don't, you'll have cut everything nice and then you'll take another path and it'll be out of sync with the other ones and you've completely ruined your threads. You got to start all over. Not good. So it's really important that you have that point exactly in the right groove, and it needs to be synchronized with how it went last time. So that's what this is all about. My air conditioner just turned on, so I'm gonna have to speak a little bit louder. The purpose of the threading dial is to let you synchronize your carriage. To back up the carriage, you have to undo what's called a half nut so that the connection between the carriage and the lead screw and the spindle is disconnected. Then you slide your carriage back, and then when you reconnect with the half nut down onto that lead screw, you want that connection to be at the right spot so that the thread is intact. All right, let's see if that makes a little bit more sense. I'm here in my design software, which is OpenSCAD, and this is a little model of a 1 thread per inch. I've never seen such a thing and it looks ugly, but let's notice, and I'm going to go up now to 2. It's a little bit starting to look a little bit more recognizable. Okay, so 1, 2, 3, 4. If you notice here that because it's 4 threads per inch, this height here is exactly 1 inch. Because it's 4 threads per inch, at exactly 4, it would repeat the pattern. If I were to take another way and then set it up on top, it would be exactly the same. And you see, it just completely repeats. These things don't change at all. So my point is that when you are threading with imperial threads and you do something threads per inch, per 1 inch, then the pattern repeats. And so as long as you are at a 1 inch boundary, the threads will always match up. Here's the threading dial indicator on my little lathe. And as the carriage goes forwards and backwards, you can see that's rotating. So it gives an indication of how the carriage is moving. This thread dial gear is going to press up against this lead screw just like it did on my little lathe. This lead screw is 6 threads per inch. If I had 6 teeth on here, every time the lead screw goes around 1 time, this advances by 1 tooth. So if the lead screw went around 6 times, this would go 6 teeth. And if I only had 6 teeth on there, then 6 teeth would be 1 complete revolution. So if you had a little indicator on the top and you had a mark, every time it went 6 rotations, or every time the carriage went 1 inch, it would have gone a full time around. But that probably is going to be moving too fast. And so what's traditionally done is you'll have 4 marks, and you could maybe have more. And so you're going to have 4 times as many teeth on here. So since we said 6 teeth would be 1 revolution, if you wanted to have 4 marks, you would make 24 teeth. So you'd go 6 and would have gone a quarter, another 6, another quarter. So by the time it loops all the way around, that really would be 4 inches. And that's what's traditionally done. This is how the gear interacts with the Acme thread. You can see as it comes in there, those teeth don't really match up. Again, I don't think they can, because this is not an involute. It's not meant to be rolled in and rolled out. Most Acme threads have a nut, and it's just going to go left, right. Another issue is there's a gap here, which is for that power transmission. So I worried that maybe it was going to lose its count when it would go past here. But I think because this is mounted, and it will be just very briefly in space, and it won't be moving during that time. But I think that when it comes back, I think it's just going to go directly into the slot across the edge of that gap. I was trying to decide if there would be a different thread gap, different distance between the teeth that would work better. To me, that looks right. Again, it's odd to me why 20 threads per inch on the spur gear matches up with 6 threads per inch on this other one. If anyone knows why that is, let me know as a comment. I create it by first generating this object, which I then use to subtract away from a disc. So I'm kind of considering this a little bit like a hob. If you look here, you can see that there's 1 gear from this one. Each one of these segments is 2 teeth wide. So one of them will be right at this angle and the other one will be at that. Now, if you're really hobbing something, the hobbing process is continuous. But I've tried doing more segments and it makes the rendering process much more slow. It's not perfect and I'm not sure exactly what I'm doing wrong. So let me show you each of those individual segments. Each one looks like this, 6 threads per inch. All right, I'm gonna try printing it out and see if it works. I think this is my final piece. I've got a place for a captive knot and it fits perfectly. The angle, the radius of that matches this exactly, and it's got a wide enough thing that it'll gap over that. So I think that's gonna work. Here's my first prototype of the thread dial indicator. Right off the bat, I had a printing mishap, so there was not good adhesion between this part and that part. Kind of cobbled it along and got it to finish the print, but then it broke afterwards. So I'm just gonna take this off, but this is right where the dial would go. Next, I can see that this arm is too long. There are 2 bolt holes there. So if I'm gonna have this and it's going to pivot on here and it's gonna lock with this, then that means these 2 pieces would need to be connected. So I'm thinking what I'll do is after I manufacture this with metal, then I'll probably come back and maybe put a little bit of weld along there. The other thing I've noticed is if I do put a locking bolt in there, I'm not sure if I can get it in. There's not hardly enough room, and especially if I make that arm shorter. So I may have to get a little something that's a little stubby. So that's the reason I make these prototypes, is so I can see how they work. But what is cool is that the gear seems to work. So this is the 3D gear I printed. I'm just gonna put it up in here, and I have a place there for a bearing, but for right now, we'll just stick it in there, and that's about the right height. And when I put that on here, when I screw in this bolt, it does come right up against there. But it rotates. Here's version 2 of the thread dial. And I like it so much, I'm not even sure if I'm going to replace it with a metal one, because it looks pretty good. I decided that I was going to let the pivot be here rather than try to fix this to this and then pivot the plate. I decided I would just pivot here and then tighten it down, and that holds it pretty steady. So there's really no force on that thing. I have a rod inside a bearing, and the shaft inside the bearing is thinner than the bearing, so I think I may take it out and put a little bushing just so that that won't have that wiggle. But even that doesn't really matter. I like it a lot. My goal is to make a part that looks like this, at least this vertical part. So I've turned down a solid cylinder, and I've got it to approximately 1/4 inch steel, and I'm going to try to weld those two together. Every time I weld, I have a wonderful opportunity to feel bad about myself. Let's see if it'll hold true today. I'm actually much happier about this than I thought I would be. Now, normal welders just weld, but only special welders do the weld and then grind method. I'm joking, obviously. I grind it away because it looks ugly, but I think I've got enough coverage there that it will hold. I've got a few inclusions. You can see little tiny defects there, but with my welding skills, I'm happy with that. This is a little welder I was using, about 120 amps DC electrode positive, and that is a 6013 rod. I bought some 7018s, but they're awfully big. I didn't really realize I'm using these old rods, which I inherited, probably 50 years old. It says 6013. I'm gonna roughly cut it to size. Not the most beautiful thing ever. I have this square, but this disc can move, so I'm gonna go back over to here. I recently went with my family over to the Blue Ridge Parkway in North Carolina in the Balsam Grove area. It was raining on the way over there, and I thought it wasn't going to work out, but when we got there it cleared. There was the clouds down in the valley. We were up above some of them. It was just gorgeous. And here are our pollinators busy keeping our world running. This is how this is going to work. This goes here. This piece will fit in here, and then this will go like that. So I'm making this in metal. So one of the factors is that I don't want it hanging out over here. So this is going to be bored out for the screw. So that needs to go over there and that, and I think that that is good enough. So I am now going to work on making this thing look nicer. Okay, I've got this part. I'm going to put it in the lathe and I'm going to face off the back side so that it's perpendicular to the shaft. Yeah, it's bowed in the middle where all that heat went in. We're getting there. I'm going to do a center drill, start that, drill that through, and then enlarge it. Okay, I've got a hole that goes all the way through there. There's my bolt, my 3/8 inch bolt, fits nice. I counterset the base. Now I'm going to see if I can get a mandrel to go up in there so that I can then flip it around and dress up that outside. All right, I've got this little mandrel. It's not very high quality, so I don't know that I can put too much force on it, but you put it in there and then you tighten in that set screw and that pushes out the sides to make it hold. So we'll see how this does. I've got to come up with a better solution for this thing. It's such an awkward piece and it's flopping around and yeah, see, that just started spinning right away. Try it one more time, but I don't know if that's going to work. I'm trying to match the angle here with what I think I might be able to try to clean up a little bit of an angle there, but with that thing being on a mandrel, it's probably a fool's errand. I might be able to put it on a bolt with a nut on the end. That's all going to be very hard metal because it was welded. It's basically, it is weld, so I don't know whether that'll work or not. First touch of metal and it spins. All right, I have some threaded rod, 3/8, some nuts going through there, tighten down. I'm just going to see if I can level out that bevel just a bit. It's not doing much. It's cutting a little bit. That's actually looking pretty good. I think I need to make my angle steeper though. There it is so far. I have to say that it's pretty ugly ugly. But on the other hand, I'm kind of proud of it because I did weld something together and looks like at least I think I've got good union there. Now, a couple problems I've found. When I put this in and drilled the hole through and everything, I think the hole wandered just a little bit because just looking at it, looks like the walls on one side are a little bit thicker than the other. And when I put it on here and then rotate it, it sticks at one way. So the main way that this is not going to rotate is through friction and force this way, where this is going to get jammed in. So I think I can just take down this diameter and give it a little bit more play, because this is all, and this is 3/8 and that was a 3/8 inch end mill, and so I think I just need a little bit more tolerance. So that'll be, probably have to put it back on here and take down this diameter a little bit more. So I'm back and I've worked on this some more. I set my compound at a steeper angle, and I had an indicator so I could always come back at a given distance this way. I then used the compound and I found where I was right at 0. So I would go in at an angle and then I could come out to take off the face. So I did a face, I go in a face and up at an angle. And with that, I've got both a nice bevel and I got the surface all cleaned up. So I think that looks real nice. So you can see I got a couple little defects where my welding wasn't perfect, which I've already mentioned, and I'm happy with that overall. And there we are so far. I need to make this shorter. This is the arm that the thread dial is going to hang out on, and it really only needs to hang out as far as it needs to clear this. And then this was a prototype where I was thinking this part was going to rotate, but instead I'm going to just put a single hole and then any pivoting will occur here. The pivot will be to rotate the thread dial so it's in contact with the lead screw. So I got to tell you a story about making this central housing. I designed this as a 3D part and I printed it out, and I was using that as just kind of a rough model because none of these dimensions were critical. But when I was machining it, and this all was down at Knox Makers, and unfortunately I didn't catch any of it on film, I was doing this inner area here, and I had put this bevel here, and I actually ended up bringing this so close to here that the top just fell off, and so that was frustrating. So then I had to put it on, and I spent a good part of a day, or my working time for a day, trying to weld this all back on, or I did weld it back on. Then this piece and this piece were at an angle to each other because it warped a little bit, or it didn't get welded on straight. So I had to machine it and had to take a good couple of days trying to get all of this stuff looking nice and smooth and concentric again. So the moral of the story is, even if I am working on something that the dimensions aren't critical, I don't always remember which dimensions were critical, because in this case, that part right there was. So from now on, I think I'm going to try to put some dimensions on my drawings so I'll not make that mistake again. So here I've got it set up in the Bridgeport. You can see those V-blocks just barely reach from bevel to bevel, and I had to really secure it tightly to make sure I had a good firm hold. Now I'm initially coming in with the X-axis and just taking light cuts, and once I get close to the end, then I'm going to do vertical cuts on the Z-axis to just make that curve all one continuous smooth surface. And I designed that curve such that it was the same diameter as the cutter I had, so that it could then come in and go up and around the lead screw on the lathe. All right, let's take our final cut, 375. All right. It exactly laid up with my layout lines, and I think that's exactly the way I want it. So I'll just have to take that out and figure out how to get that deburred in there. All right, here I've got it cleaned up, polished it again. That looks good. Now I'm going to work on this. That brass is from an old gear, which I finished off, put a hole in the middle. Then I got a piece of steel for the base, turned it and made an interference fit, which I got together on the press and got the two like that. So I've got long grooves and short grooves marked. I'm now going to put a dot And it's going to be 1, 2, 3, or 4 dots by each of the long lines. I can't really show it and do it at the same time, so I'll have to show you when I'm done. So I put 1 dot on each one, then I've got 2 dots on 3, and I'm going to put 3 dots on these 2, and then 4 dots on this one. And there it is. It's not perfect, but it'll do. Okay, we've reached a point of no return. I'm cutting it off from that holding block. Parting off always makes me anxious. Now if you notice there's a lot of run out in that front dial, and I previously had got everything all indicated in nicely. But since I'm just parting off the back side of this, I didn't feel like it was worth redoing all that. I couldn't cut and show at the same time because I don't have a tripod, but there it just came off. Well, I think when I drilled with a 1/4 inch drill, I think it went a little oversized. And I think this shaft that I'm using is a little undersized, because when I put it on here, there's wobble. And then if I tighten it, you can see that it still moves. And then it wobbles a little bit there. So I may need to make myself a new shaft that's just a little bit bigger. Okay guys, that's about all the footage I was able to capture on this project. I did end up making a custom shaft, and I made it a little bit wider than the initial 1/4 inch that I had planned because I wanted it to have a nice fit with those bearings. At one point I had to get my little lathes 3-jaw chuck because my big lathes would not close down all the way to the size of that shaft. So I put the 3-jaw chuck in the 4-jaw chuck and then got it indicated. I didn't want to cut on the mini lathe just because it doesn't do a real good job. So I'm happy with how the whole thing turned out. I think it looks real nice and polished. And here's the final product. I probably need to put a coat of paint on it at some point to keep it from oxidizing, but right now I think the shiny metal looks good. So we'll leave it that way for a little bit. Here's a puzzle for all you machinist wizards out there. The lathe at Knox Makers has 8 threads per inch, whereas mine was 6. And its gear at the bottom of its threading dial is 24 teeth, which means that a complete revolution will go 3 inches rather than the 4 inches that I talked about. And yet its dial has 4 markings. That means that at the 1, 2, 3, 4, at this number 2, that'll be 1.5 inches, and at 1 mark, that would be 3/4 of an inch. Now this makes no sense to me. It doesn't seem how you're going to be able to get your threads to line up exactly. The plate that has the instructions looks like this, and Billy has tested it and says that at least for the threads that he tested, it seemed like it was working. So if someone can explain the math about how that works, I would be very grateful. Okay, that's all we've got for our video today. Thank you so much for watching. If you enjoyed this video and if you got this far, I hope that you can give it a thumbs up and maybe subscribe. This is going to be the end of the lathe series. These videos take an inordinate amount of time to edit. I think this one has been probably about 12 hours so far. And I've got a lot of the other stuff that I need to get caught up on. So I can't promise when the next video will come out, but if you stay subscribed, then when I do get some content out, it'll be there for you. Thanks so much for watching. And I don't know if you ever watch Mr. Pete, and he talks about his neighbor doing spike mowing. Just when I'm videoing this, out comes the mower. So anyway, thank you so much for watching. Have a great day.
Bye-bye. Have a wonderful time.
Peace out.